Hello students, so far we have read about the fields separately and potential separately. We have defined field and potential with respect to their definitions, like field is denoted by E along with a head arrow, which shows that electric field is a vector quantity, and potential is defined with the abbreviation as V. Electric field is given as kq upon r square, whereas potential is given as kq upon r. E shows a relation which is inversely proportional to r square, whereas voltage shows a relation which is inversely proportional to just r. So when we draw a graph between E and r square, it comes like this, and whereas for potential it is a straight correlation. So these are the two different entities which are bound together because of the electrostatics we are reading. Because we are reading electrostatics, so these got bound. So how these two fields and potentials are related to each other, and if they are related to each other, how they can help us to understand electrostatics better will be read in this section. The section's topic head is relation between field and potential. So here in this topic we aim at knowing what's the relation of field and potential, not field alone and potential alone, but their relation, fields and potentials relation. For that, basically what we did is we have defined equipotential surfaces, because it is easiest to provide relation to the equipotential surfaces. We will see if the surfaces is not even equipotential, what will be the result. So this is one of the equipotential surface. We can say that this is surface 1, and below is the another equipotential surface. See over this green colored, this is another equipotential surface. From this equipotential surface, we have taken the center of both of it. Center of both of it. See, center of this is this, and center of this is exactly over like here. So from here we have our electric field line is passing from center. Okay, and the distance between these two equipotential surfaces is del L. Distance between equipotential surface 1 and equipotential surface 2 equals to del L. So first of all we have given defined like electric field over here. Then by understanding the distance, we brought a test charge Q. This is a test charge from infinity, because what is potential? Potential is the amount of work done needed to bring a test charge from infinity to a distance of r from our reference charge. Okay, so here the reference charges are present on these equipotential surfaces, and from this infinity we have brought this particular charge here. This charge came in contact with this potential surface first with V, then this charge will move a distance of del V. Like in this particular distance, the amount of potential the charge will feel is a minimum potential, that is del V plus, that is extended. This is V, this will be also V, but because there is a difference of some distance, this some distance will create a very minimal amount of potential. So that is added over here. So from equipotential surface 1, it will face a potential of V, whereas from equipotential surface 2, it will face a potential of V plus del V. So now we know how we are getting electric field, we know how we are defining potential here. Our now main work here is to relate this electric field and this potential which we have so far calculated. Coming to the point number 1 over here, the relation between electric field and potential, that is E and V, is similar to that of relation between gravitational potential and the field. Gravitational force do create a field and a potential, as we have read in class 11th. In a similar fashion, V and E for electrostatics is also related. Like whatever the field is there when we consider gravitational force, it to have components like potential and field lines. In a similar way, our electrostatics or electromagnetic forces also have such components. Like electric fields and electric potentials, and they have the similar relation as our gravitational force do have. The relation between electric field and potential is generally given by electric field is the negative. Whenever our electric field is negative in the opposite direction of our electric field, potential is defined. Now this statement is little complicated over here. Why? Because so far we have just given a definition. We haven't verified, we haven't proved. So let's start with the proving. How is it negatively related to potential? How is electric field negatively related to potential? Now see, let's consider two closely spaced equipotential surfaces A and B with potential value V and V plus del V. Okay, now del V is the change in potential in direction of E. This del V is the change in the direction of E. Taking a point P on the surface B, del L, this is the distance, okay, perpendicular distance of surface A from P, from the point P, okay. Point P is on surface B, okay. I'll write here point P is on surface B and del L is distance from surface A to P. That implies from surface A to surface B, okay. If Raju stays in his parents' house, that does not say that this is his parents' house or his house. Like see, if you are staying with your parents, is the house belongs to your parents or to you? It belongs basically to your parents. So Raju is staying in his parents' home. The distance between his parent and your parents' home is x centimeter. Now just think, what is distance between your house and Raju's house? Similar, because as you two, your parent and you, stay in the same house, the distance of the two houses is going to be same. In the same fashion, see this diagram over here. The point P is on surface B and the distance of A and P is del L. So let it be anything. We can say that distance between equipotential surfaces A and B is del L2. Okay, that is as similar as to the example so given. Now let's bring a unit positive charge which moves along the perpendicular from surface B to surface A. against the electric field. Now see, here comes a twist. We got a test charge over here, TCQ. Okay, this we are bringing in this direction, okay. This test charge have a direction opposite to that of the electric field. Test charge have a direction opposite to that of the electric field. Now what we see here is that now this concept of negative electric field or negative potential comes under the game. So see, work done in this process is E del L. So first thing, why we are bringing our test charge into here, test charge Q, it is brought to define potential, Secondly, work done is given as the electric field into the distance. Work done is given as electric field into the distance. So this is electric field and the distance between the two equivalent surfaces is del L. I have already explained how come we found this del L. Now this work equals the potential difference VA minus VB. How do we define work? According to the potential, work done equals to change in the potential V, that is VB minus VA, or vice versa as per to the requirement or negative signings. So this work done from this equation, we can name it as equation 1. From this equation and from this equation we will get this relation. What is the relation? Relation is work done E into the distance between the two equipotential surfaces is equals to VA minus VB. What is VA? VA is just V. See, this is our A. This plate is our A. This plate is our B. So the distance between A and the potential difference between A and V is V for the A and V plus del V for surface B. Okay, so that one for A, and for B we will get V minus plus del V. Now we will extend it. The minus will go inside the bracket and the answer we will get is V minus V minus del V. This V and this V will cancel out because they have the same magnitude with opposite signs, and only this will left. What is it? It's a negative value. It's a negative value. Now our E is defined with respect to this negative value. This L which was present over here from the very first step will move towards the right hand side, and the equation we will get over here is, just 1 minute. The equation over here we will get will be E vector equals to minus del V upon del L. Okay, see over here we have taken a modulus because electric field lines cannot be negative, and this is related with the change in voltage and the change in distance by this relation. E equals to del V by del L. Though you will ask a question that this is not the final formula, why is it important? It's important in the case when they have given you the difference of potential between the two equipotential surfaces for a given separation between the equipotential surfaces, and they might ask you to find the work done, to find the potential, or to find the electric field, anything. But once you find electric field, you can find the work done as per to the given relation, that is work done equals to electric field into the separation between the two surfaces. You can find next our potential also. The potentials relation we will see up in this particular topic at all. Okay, so just moving to the next step. Here electric field, we have found that it is equals to minus del V upon del L. Now we took a modulus or the mod for what? For del V, so that we can eradicate the negative polarity or the negative sign. Anything you can write, negative sign from here. So this is what we have got finally. Now we will redistribute this equation and integrate it. Over here you can see it's been getting integrated. It's been getting integrated. Now see, I will solve it up for you all. See over here, E equals to minus del V upon del L. Now E del L equals to del V, integrating on the both side. E, we will take minus to this side. E del L equals to integration over del V. Now this will remain same, come over here, minus E del L equals to dV upon VA upon VB. Now it will be VA minus VB equals to minus of E del L. So we can do one thing over here, is that we will take a minus out and our equation will be VB minus VA equals to E del L, or we can keep it as such, no need to make any sort of changes unless until it's required. Okay, now this change in the potential across the equipotential surface A and equipotential surface V can be simply stated as del V, no prefixes and no suffixes. Now we will see the three different cases when we have related electric field lines and potential. We got three cases. In the first case, it says that if the test charge is positive. In the second case, it says that if the test charge is negative. And in the third case, it says that neither it's positive nor it's negative. It belongs to an equipotential surface which is having equal potential. Then what happens? Okay, now see, the test charge is positive in this case, case number 1, then potential gradient will be more near the charge. Potential gradient will be more near the charge. Now see, this is our Q plus Q, test charge, and it is nearer to our Q. So it will have more of the potential, because the potential near will be more and later on it will keep on decreasing. V is related to R in such a fashion, V equals to 1 upon R, whereas our electric field is related to R in a such a fashion. See, E equals to 1 upon R square. They exponentially decrease down and they linearly decrease down, linear decrease. Now, case number 2, when the charge given is negative, potential gradient will be more as we move away. Now, our charge is negative. So, when it is positive, when we will come near, potential will increase. I will write over here so that it will be more clear to you all. Okay, see, our test charge Qt equals to positive, and this is our this one. So more nearer, more potential. Okay, near equals to more potential. Now our test charge here is a negative test charge. So this have this one. This charge started moving away from it, away. When it started moving away, it found out that away it is, more is the potential, more is the potential. Now you can remember it in such a way that whenever someone tries to provide you the positive aura or the positive energy, what you feel is having more potential to do work, you become more energetic suddenly, and you can do your work more efficiently. So in similar way, when our charge Qt is positive, it will have more potential near the capital Q charge, because our Qt is positive right now. But in case our Qt becomes negative, what will happen? Once you will become negative, you will start moving away from the people who tend you think, who make you think such things. Okay, so just think, your mother scolded you, what you will do for a whole day? You will stay away from your mother, you will show that you are angry. Okay, so in same way, Qt became negative now, and it will start running off from the charge Q. Once it will start running away from the charge capital Q, what it will show? It will show more potential at that point. Now the third case is a more interesting case. Here neither we have positive nor we have the negative. We have equipotential surfaces. The potential at every point on the surfaces will be same. Thus potential gradient will be 0. V across the equipotential surfaces is 0. This is quite an important point which should be made a note of. So I'm writing it with a green pen. Kindly write it up so that whenever you refer your notes for a quick revision, it gives you all the information and it's handy too. So write it up. When we have equipotential surfaces, potential gradient between two is same or not changing. Okay. Now the two important conclusions we have derived by the thorough studies. Derived by the study. Okay. Now see, the conclusion number 1 is E in the direction in which potential decreases steepest. E always moves in the direction where potential shows decrease. So E and V are negatively related. Negatively related. We have seen it even in the derivation. Now the second option states its magnitude is given by change in the magnitude of potential per unit displacement normal to the equipotential surfaces of the point. Now the magnitude of this particular electric field and potential is taken as the magnitude of potential per unit displacement. This is our equipotential surface 1, and now this is our equipotential surface 2, which are just away by a minimum of the distance which can be in mm but not more than that. Can be in mm but not more than that. So the change in this particular magnitude along with the displacement and that is normal to the equipotential surface as well as electric field, is what they calculate, is whose magnitude they tend to calculate. Now see the purple-lighted point. Electric field will be perpendicular to the direction of electric field lines. Electric potential, not the field, kindly understand it. Electric potential will be perpendicular to the direction of electric field lines. V and P have perpendicular relation. Have perpendicular relation. So this is quite an important thing over here. We will just make a quick summary where I will not write and just give you the verbal summary. Here in this topic we have understood the relation between electric and potential field. Electric and potential fields are negatively related to each other, and the electric field with respect to potential is given as dV equals to minus EdL. Here dV can be written as the potential difference across the equipotential surface A minus the potential across the equipotential surface B is given by the negative of the product of electric field and the distance between the two electric equipotential surfaces. And here we have found that the direction of E is in the decreasing potential direction, and the magnitude of our potential per unit displacement is normal to the equipotential surfaces. And then the most important thing, electric potential and electric fields are perpendicular to each other. Electric potential and electric fields are perpendicular to each other. So that's all for today's class. We'll meet up in the next class with a new topic and new and as well as interesting topic from the same chapter. We'll see you in the next class. Have a good day. Bye bye.